All right. So I'm going to start with just two examples of why we care about this.
Is this 4 or 5?
Yeah.
This is 4 or 5. Thank you. All right. So parametric equations are used a lot because we often have things that are a function of more than one thing. So temperature is a function of time and location, right? Location being, all right, we're here in Orinda, but temperature in the morning is going to be different than temperature in the afternoon, different than temperature in the fall, winter, spring. So it has two parameters that really dictate what happens with it. So temperature is a function of two parameters. We also have, like I talked about really briefly, projectile motion. So for the physicists in the room, if we shoot something off and it only has an initial velocity, it follows what shape? A parabola. So you have a velocity, and any point in time is dependent on three things. It's dependent on your initial velocity, the angle that you shot it up at, and then the last parameter is time. So how long it's been in the air. These are called parameters. So this pops up a lot. The book does a pretty poor job of giving you examples. It really focuses on an ellipse. But down the road, if you take economics or something like that, more of a social science, you'll have a lot of parameters. You have equations with different parameters that you have to use. So that's kind of the overview. If we get into the specifics of it, here would be an example. So I have x and y both defined in terms of another variable. So what's the parameter in this case? T. Okay? So everything is defined in terms of t. And there's three things that we can do. One is we could get a graph. Okay? The problem is that if you try to plug it into your calculator in normal mode, how many variables do you have places for on this calculator in regular function mode? You have y and you have x. So if you try to just hard code in a t, it's not going to know what it means. So we'll look at how the mode changes in a minute. So you could graph it with the calculator, but you need to change your mode to parametric mode. So now we have degree mode, radian mode, and parametric mode that we're going to deal with. Down the road, we're going to have polar mode as well. We could also make a table. So the way you learned to graph things back in 7th grade still works. Okay? I can make, instead of an XY table, I'm going to make an XYT table. And I can get my points that way. So if I start with an XYT table, this becomes pretty tedious if the equation is complicated, or if I need a very fine-grained amount of time, or in this case, t. And the last one, it seems a little silly to talk about parametric equations, but we can get rid of the parameter. So we can get it just in terms of x and y and use our regular function mode and the way that you guys are used to things to get rid of the parameter and deal with just x and y. So those are the three things that we're going to do. The calculator is not too bad. The table takes a long time. Most of our time will be spent on eliminating the parameter. Okay. So we're going to use our identities to get rid of t. And this is the one that I'm going to use. What's that one called again? Pythagorean identity. So I want to get somehow to cosine squared t plus sine squared t. And I know that's equal to 1. So my first step is going to be to square everything. And I get quantity x minus 4 squared equals cosine squared t, and quantity y minus 2 squared equals sine squared t. So I'm very close. Now, can you distribute this exponent? Can you get, is it x squared plus 16? No, please don't. We have to write it out. X minus 4 times x minus 4. And we could then combine them into our Pythagorean identity and get x minus 4 squared plus y minus 2 squared equals 1. All right. What shape is that going to give us? I hear some mumblings. It's either going to be a circle or it's one of our conic sections, right? That we'll have down the road that you had in Algebra 2. So we have an ellipse with minor and major radiuses of 1, which makes it a circle. Okay. Where would the center be? Anybody want to guess?
4, 2.
Great. All right. All of our transformations that we had before for the sine graphs, vertical and horizontal, still work here. So this would be a center at 4, 2, and we'd have a circle with a radius of 1. All right. So that's one way that we could do it. Why couldn't I solve for things with inverses? So what does that mean? If I solve for t, is that valid? Is that the way to do it? So what I did is I subtracted 4, and I had cosine of t equals x minus 4, and then to undo the cosine, I took cosine inverse. Does that sound legit? It does, right? So that should work. And then I can do the same thing for sine of t. So I get those together, and what can I do if t equals both of those things? You can set them equal to each other. So I could go like this. And if I wanted to solve for y, how do I get rid of the sine inverse? Please don't say divide by sine inverse. As already looks like sine inverse and arc sine are similar. Sine, right? The inverse of sine inverse is the function, is sine. So if I take sine of both sides, I get that. I can solve for y. Now, two things. First off, that's complicated, right? I have sine of cosine inverse, so I don't really know what that is. But theoretically, it should be giving us the same picture. But it doesn't. Because remember our bounds on cosine inverse, I only go between 0 and pi. What is the sign, the value, positive or negative, of sine in that interval in the top half of the unit circle? So if I look at just this piece, the top half, am I getting positive or negative sine values? Positive. I'm getting positive and negative cosine values, but only positive sine values. So if I put this in, I have this restriction, and it turns out that I only get the top half of my graph, because I'm only getting positive sine values. So instead of a circle, right, I'm going to get half a circle. I've lost my bottom half because of the restriction on cosine inverse. So if you solve it that way, you're only going to get half the picture, which is why we use our inverses. Okay, are you with me so far? Mm-hmm. All right? Okay, good. So the books throw this in here, and we'll talk more about it next week too, but for whatever reason, it gives you just the parametric equations of an ellipse and lots of pictures with ellipses on it. So we have x equals h plus a cosine t, and y equals k plus b sine t. If we were to use our Pythagorean identities and solve for t, we would get your familiar conic section for an ellipse. And again, remember an ellipse looks like that. There's my center, and I have major and minor axes. So we'll talk more about this next week. I really want to just get the big idea of parametric equations out there so we can see kind of how they work, what they're doing, and then look at the calculator as well. All right, let me write this down. Okay, so on your paper, you can go ahead and turn it over. So this is an example. It has a little brief overview of why we use parametric equations or functions. And we have an example here for x in terms of t and y in terms of t. And we're going to use a table. And I've given a domain for t from -2 to 2. So I just picked -2, -1, 0, 1, 2. I just decided that I was going to count by ones. So once I've done that, I plug in values for x. I plug in values for t and I get x and I get y. So I plug them into t squared plus 1. And then I plug them into 2 times t. Now if I'm graphing it, what are the only two variables that show up on the graph? X and y. So t is not there explicitly. I just have x and y. So if I plot those points, I'm looking at the ordered pairs right there. So those are the points that get graphed. So when you're graphing them, you're not going to have t show up. But I get my points there. And then are those discrete or can I draw a line between them? How do you know? You can't? You can? I don't know. It's one of those, right? What are the values of t that work? -2 to 2. Are these the only numbers that go from -2 to 2?
No.
No. How many are there? More than 5, right? Okay. So this is called our t-step. I'm stepping through the interval by an interval of 1. But I could have gone by 0.1, I could have gone by 0.01. That's why the table is bad, because I'm never going to get all the points. So this line does get connected. That's what I was doing. Looks like that. Does it go past these 2 points? No. Because those are my biggest and lowest bounds on t. So it is like a parabola, but turned on its side. And our general equation, if we wanted to solve for it, if we wanted to get rid of the t, eliminate the parameter, I would solve for what? Solve for t, plug it in, and you get x is y squared over 2 plus 1. So this is pretty simple. Down the road next week, you can give them word problems and have to write some equations. But this part's not too bad. All right? All right. On the back, I want you to try to eliminate the parameter for those 2 equations, and then for the ones below it as well. So it'll take about 5 minutes, and then we'll go through my solutions and see if they work. First one, I have x squared equals t. It's just one step to eliminate. I just plug in x squared when I see t, and so y equals 1 minus x squared. So the parametric equations, if you're in parametric mode, give you this shape, and this shape is a parabola, right? It's been flipped over. So it's a complicated way to give the equation of a parabola. The next one, you want to solve for cosine of t and then square it. Yes?
I ended up with, because x squared equals t, I just moved t over on the y and then subtracted y on the other side.
Sure.
But that leads you to 1 minus y equals x squared. Does that work as well?
Yep. If you added x squared to both sides and subtracted y, that's what you get. Yep, that's fine. So the next one, I divide by 4 and I square everything. And then I divide by 6 and I square everything. And I can relate sine squared and cosine squared with our Pythagorean identity. So that equals 1. And then I just substitute. What is this shape? Right. So this is, conic sections are, I get really frustrated with them. But we don't have to deal with them for a while. But really all we're dealing with is an ellipse in this chapter. But we can solve it that way, and then we could graph it. If we wanted to solve for y, we could do that as well. But again, don't use the inverses. If you do, you're only going to get half the story. You're not going to get the full thing. All right, let's look at the calculator, and then I will let you guys work on the problem set. So I know that all of you don't have a calculator. Raise your hand if you do have a graphing calculator. Okay. All right.
Okay, good.